Another approach to working with conic sections, parabolas, ellipses, and hyperbolas is called the eccentricity and directrix approach. So we're going to start by letting line L be the directrix and point F be the focus. And it's important to know that point F is not on line L. The eccentricity is some real number that's positive. And we use a lowercase e, not to be confused with Euler's number. Okay, it's a totally different context. But we do have a real number e that is called the eccentricity. The conic section, the graph of our parabola, ellipse, or hyperbola, is the set C, which is the set of all the points in a plane, such that the distance from the point P on the curve to the focus is equal to the eccentricity of the distance from P to L. Now, this distance, PL, is the perpendicular distance from P to the line L. Okay, another way of looking at this relationship right here, it could also be written, and this I think is a little more useful, the distance from P to the focus divided by the distance from P to L equals the eccentricity of the graph. Alright, so let's look at this parabola. I have a fixed point L, a fixed point F, and a fixed line L. And if I pick P, some point on this curve, and measure the distance from P to F and measure the perpendicular distance from P to L, so that makes a right angle, and that's going to intersect line L at point capital L. With a parabola, the distance PF divided by the distance PL will equal E, and that will always equal 1 if you have a parabola. Okay, and that goes right back to the definition of a parabola. By definition, a parabola is the set of all points equidistant from a fixed point and a fixed line. The eccentricity of a parabola is 1. Now, with ellipses and hyperbolas, there's always timeout, pause. Alright, sorry for that quick interruption. Alright, where was I? Ellipses and hyperbolas are going to have 2 directrix lines and 2 focus points. So to talk about the eccentricity of those graphs, I'm going to focus in on what's going on with 1 line and 1 point. Alright, so let's see, where point P is some point on the graph of this ellipse. The perpendicular distance from P to the line L is there. The distance from P to F is there. And that intersects line L at point L. And we can say the distance from P to F divided by the distance from P to L is equal to the eccentricity. Now, look at those distances. The distance from P to L, no matter where you are on this ellipse, the distance from P to L is going to be just a little bit longer in some cases significantly longer than the distance from P to F. So you're going to have a fraction here where the numerator is smaller than the denominator, which makes the eccentricity some number less than 1. Alright, now we are picky. Eccentricity is always a positive number. When we move on to hyperbolas, Again, we're going to have to pick 2 points P because there are 2 kind of branches to this hyperbola. So let's say point P1 is here. If I measure the perpendicular distance from P to F, P1 to F, sorry, that's not the perpendicular distance, the distance between those 2 points, and the perpendicular distance, there we go, from P to point L1, and then we also have to have a second point on the other branch, somewhere on the other branch of this hyperbola, so we'll call it P2, measuring the distance from P2 to F. I tell you what, let me use a different color. That'll work. P2 to F and P2 measured back to the directrix, and that's going to be a right angle there, and that's going to intersect at point L2. Okay, it is true that the distance from P1 to F divided by the distance from P1 to L1 is equal to the eccentricity. Now, in this case, the distance from the point to the focus is longer than the distance from the point to the line. So we have a value on the top that's greater than the value on the bottom, making E a number greater than 1. Same thing's got to be true for the second point. So P1 to F and, P2 to F and P2 to L2 has got to be equal to the eccentricity E, and E has got to be greater than 1. Now, let's kind of try to organize what we know here. For ellipses and hyperbolas, centered at the origin, I'm going to kind of put this together in a chart so it's easy to look at. There, of course, are 2 options. You can have foci on the x-axis, or you can have foci on the y-axis. The major axis vertices will always have, if the foci are on the x-axis, major axis vertices are always going to be a units away from your center. So if the foci are on the x-axis, then you're going to have plus or minus a, comma 0. Your vertices will be on the x-axis. If your foci are on the y-axis, your vertices will be on the y-axis. So 0 plus or minus a would be the coordinates of those vertices. Now, your minor axis vertices, and we haven't really talked about them as vertices, so I'm kind of going to put this in quotes. They're not really vertices of the curve, but they're points that we use if we're sketching the curve, so we need something to call them. Those are going to be b units away from the center point and going to be on the opposite axis of where the foci and other vertices are. So 0 plus or minus b would be the correct coordinates, and plus or minus b, 0 would be the correct coordinates if you've got foci on the y-axis. Foci on the same axis as the vertices, and they are c units away. So plus or minus c if they are on the x-axis, 0 and, plus or minus c 0 if they're on the x-axis, 0 positive or negative c if they're on the y-axis. The eccentricity If the value of E, remember how you can find the eccentricity, you find the distance from P to the focus and divide by the distance from P to the directrix. If E is between 0 and 1, you have an ellipse. And if E is greater than 1, you have a hyperbola. Ah, I left out directrixes. Directrices? I'm not exactly sure how to pronounce that. The plural form of the word directrix. T-R-I-C-E-S. Directrices. If the foci are on the x-axis, then your fixed lines are vertical, and they will be at x is equal to plus or minus d. Now, d is a value we really haven't talked about yet. It comes in handy here. And if your foci are on the y-axis, you have horizontal directrices, and they will be at y equals positive and negative d. So we've got values a and b that are very obvious, that you can pull from the equation. We've got a value c that you can find if you know a and b. We've got a value e that we can figure out by looking at the ratio of some distances. And then d, we don't really know anything about at this point. But the cool thing is, if, we look at, units, okay, I'm having a hard time saying this. A, B, C, D, and E. There are 5 parameters for every conic section: parabola, ellipse, hyperbola. We're really thinking about ellipses and hyperbolas. If you know 2 of these, you can find the others. Okay. For all of the conic sections, C is equal to A times E. To multiply the value A times the eccentricity, you've got the value C. And D is equal to A divided by E. So you do the division, and that gives you the value D, which is going to tell you the location of your directrices. Then, of course, B squared is equal to A squared minus C squared for an ellipse. And B squared is equal to C squared minus A squared for a hyperbola.